In this video, we will begin learning how to solve graphical as well as analytical limit problems. Let's begin with the first graphical example. In this example, we have an arbitrary function f of x. We are asked to find f of 2 and the limit of f of x as x approaches 2. Let's begin with f of 2. According to the graph, there is actually no y output for the given x input of 2. Therefore, f of 2 simply does not exist. The limit, however, does exist because in limits, rather than finding the actual value at a certain point, we find the values approaching that point from both sides. So in this example, we are looking for the values a little to the left and a little to the right of 2. A little to the left of x equals 2, such as x equals 1.99, we get a y output of 1. Similarly, a little to the right of x equals 2, such as x equals 2.01, we get a y output of 1. Therefore, we can say that the limit of f of x as x approaches 2 is 1. As a side note, rather than checking f of 1.99 and f 2.01, we can notate this more correctly as follows. The limit of f of x as x approaches 2 from the left is 1, and the limit of f of x as x approaches 2 from the right is 1, therefore the overall limit must be 1. The negative superscript at the 2 indicates from the left. The positive superscript here at the 2 indicates from the right. It is always useful to evaluate the limit from each side to make sure the overall limit exists. This will become more important in example 3 of this video. First, let's move on to example 2. In example 2, we have a function f of x. We are asked to find f of 3 as well as the limit of f of x as x approaches 3. When finding f of 3, the graph has a y output of 5 for the x input of 3. Therefore, f of 3 is simply just 5. For the limit, just like in all limit examples, we must take a look at both the left-hand side and the right-hand side of the x point in question, which in this case is x equals 3. From the left, the function is approaching a value of 3, and from the right, the function is approaching a value of 3. Therefore, the limit must be 3. I have put this information on the side note this time as well. In example 3, we have a piecewise function where the function breaks off, then continues somewhere else. It is extremely important to take the limit from the left and the limit from the right in a case like this, but we will get to that. Let's begin with f of 0. There's no point for f of 0, so it simply does not exist. For f of 2, the function is outputting a value of 2 for x equals 2. Therefore, f of 2 equals 2. For the limit of f of x as x approaches 0, let's imagine the limit from the left and the limit from the right exactly like we did in the side notes of the last two examples. The left is approaching 4 and the right is approaching 4. Therefore, the limit must be 4. For the limit of f of x as x approaches 2, this gets more complicated because this is where the function breaks off. It is extremely important to take the individual limits from the left and the limits from the right in a case like this. When taking the limit from the left, this is approaching 2. When taking the limit from the right, this is approaching negative 2. 2 does not equal negative 2. Therefore, the overall limit does not exist. I've included this in the side note as well. Let's move on to analytical limit problems. For all analytical problems, there are always two steps we must follow. First, we must try to plug in the given value of f of x. If this results in a non-existent or non-real answer, we move to step 2, which is first simplifying algebraically, then plugging in. For the fourth example, we begin by trying to plug in. Fortunately, this works in our favor and gives us no problem when we plug in x equals 2. We get 9 times 2 minus 3 over 2 squared plus 4. This results simply in 15 over 8. For the fifth example, we begin by trying to plug in. We try plugging in x equals 2, but we get 0 in the denominator if we would do so. We would get 2 squared, which is 4, minus 4, which is 0. Therefore, we must go to step 2 and simplify algebraically. We pull out a 9 in the numerator and we do a difference of 2 squares in the denominator. This gives us a function that we can plug into without any problems once we cross out the x minus 2. We plug in 2 and we get 9 over 4. The sixth example is actually the function of the graph drawn in example number 1. We see here that x equals 2 clearly does not work because it results in a 0 denominator. Also with example 1, we had no answer for f of 2. For both answers, however, the limit equals 1. In this example, we can cross out the numerator and the denominator to result in a simple 1. Therefore, in both instances, the limit actually does equal 1. Example number 7 is a piecewise function where the function breaks at x equals 8. This is similar to example number 3 where the function broke at x equals 2. For f of 5, since 5 is less than 8, we must use this function. Therefore, we get 7 times 5 plus 2 which results in 37. For f of 8, the function clearly tells us that when x is 8, y is 13. For f of 13, since 13 is greater than 8, we must use the 6 minus 2x function. We get 6 minus 2 times 13, which is negative 20. Now for the limit. We must break this limit into the left hand and the right hand limits. For 8 from the left, we plug in x equals 8 into the left hand function of 7x plus 2 and get 7 times 8 plus 2, which gives us 58. For x from the right, we plug 8 into the right function of 6 minus 2x and get 6 minus 2 times 8, which gives us negative 10. 58 clearly does not equal negative 10, therefore the left-hand function does not equal the right-hand function. When the left-hand function doesn't equal the right-hand function, the overall limit does not exist.